All right, our next speaker is Christopher Kremer, who will be talking about discrete spectral absorption bands in 4 to 8 micron infrared region, new tool for remote compositional assessment of Olivine FE content.
Thanks for the introduction, and thanks to all of you for being here. Today I'm going to talk about some exciting possibilities for constraining the chemistry of olivine from spectra measured in a region of the infrared that for a while has remained fairly unexplored. So the composition of olivine, as well as those of other major rock-forming silicates, fundamentally informs our models of the origin and evolution of planetary crusts. Unfortunately, for a variety of reasons, it has been difficult to interpret the magnesium numbers of olivine in remote sensing data gathered from other planets and planetary bodies, including the moon. And one of the reasons for this is that in visible near-infrared spectra, there are overlapping absorptions that can hamper confident and precise interpretations of magnesium number. And so I think that one possibility for getting a better handle on this question is to look at a region of the infrared that for a long time has not been examined in close detail. So when we think about the visible and infrared spectral range that is relevant to remote compositional sensing, we think about the visible near-infrared, or V-near, and in the mid-IR. And so the visible near-infrared, shown on the left, is dominated by spectral bands that arise from electronic transitions in crystals, and this regime is also dominated by the scattering of photons, namely body scattering of photons. While in the mid-infrared, we observe spectral bands that arise predominantly by molecular vibrations, and that is dominated by surface scattering and thermal emission of photons. And what we have just to sort of elucidate, this is a generally sort of schematic plot where on the top axis we have wavelength, and on the left axis we have reflectance. And so what I am going to talk about here is the possibility for using a region of the infrared that I'll nickname the crossover region that is basically right between these two fairly different regions of the V-near and the mid-infrared. So previous work done by John Salisbury and others has indicated that in powdered samples of rocky materials, that olivine and some other silicates exhibit strong, distinct, discrete bands in the approximately 4 to 8 micron region, or also shown in wave number on this plot. Just the same, this highlighted box is the same as in the previous one. And so the bands in this region are generally understood to arise as overtone and combination bands of fundamentals that occur at longer wavelengths or lower wave numbers, and namely arise as overtone and combinations of fundamental stretching and bending modes, which are indicated on the plot with the key as shown there. And what's particularly exciting is that the fundamentals of these bands, as shown by Vicki Hamilton and Melissa Lane and others, exhibit systematic changes in their band positions with respect to magnesium and iron chemistry of olivine. And so then the major question in this study is what changes do we observe in the band positions of olivine with respect to magnesium iron chemistry, and how do natural and synthetic pure samples compare to each other? So to that end, what I've done in this study, along with my co-authors, is compiled data from two major sources. First, the Relab database and the USGS Spectral Library. We compiled data from multiple suites of olivine spanning, for the most part, the full magnesium iron solid solution series from F force right 0 to force right 100. And all the data here are shown in reflectance. All these data were measured in reflectance, and that's a point I'll touch on at the end. And the spectra are offset for clarity. And all these are measured on FTIR. So the first thing that we see when we look at this, what we're looking at here is first a suite of what are referred to as the SUNY suite of synthetic olivines. They're some of the purest synthetic olivines that you can get, where I mean purity with respect to cation substitutions. And so what we see right off the bat is that here where the blue is the magnesium end member and red is the iron end member, we see two major strong bands that comprise a doublet that shifts systematically to longer wavelengths or lower wave number with increasing iron content. So when we then draw in the data from another well-known, well-characterized suite of olivines described by Darby Dyer, the so-called Bristol suite, which has more stoichiometric contamination, including oxidized iron. We see a similar trend. And an important thing to note is that the positions of those vertical dashed lines are consistent throughout the remainder of these plots, and that the blue and red values correspond absolutely with the relative abundance of magnesium. So it's also exciting that we see this consistency in trends, even though there are sometimes considerable impurities in these other synthetic olivines. So that was pretty exciting when we first saw that. The thing that we wanted to next see was, does this pattern that exists in natural olivines or in synthetic olivines also exist in a messier reality? So to this end, we compiled data from the USGS Spectral library, and these olivines come from a variety of sources. The data are a little bit noisier, but what we see right off the bat is that there is a similar systematic relationship with the band position of the 5.6 and 6 micron bands and the iron composition. And also, as sort of a minor note, we can also note there are these sort of minor bands that exist in the synthetic suite that also exist in the natural suites as well. So that was pretty exciting. And then the next question is, well, we have natural samples and synthetic samples. We also would like to look at extraterrestrial samples if we'd like to potentially see this applied to other planetary bodies. So we compiled data from the Relab Spectral library, and also just for note, one important thing to note that I didn't explicitly say before is that those data were all measured on powdered samples of varying grain sizes, but in the main less than 75 microns. And the same, for the most part, applies to the samples I'm showing here with some caveats. So what I've done here is I've compiled data from olivines extracted from meteoritic samples from Mars, shown in red, and 2 Apollo samples, shown in green and orange. The green colored sample is an olivine separate prepared by Peter Isaacson that comes from a basaltic composition sample, and then the orange glass is sort of the orange glass of great Apollo 17 renown. And one thing that's interesting to note is that not only do we see the same doublet that we saw before, we also see that while absorptions that would be strongly diagnostic of olivine are missing from the orange glass in the visible near infrared in the plot shown on the left, in the plot on the right, we can see the same familiar 5.6 and 6 micron bands, which likely arise from olivine phenocrysts that have been observed and characterized in the orange glass beads. So this was all interesting and very promising. The question now is, now that I've shown you all these plots, how do the band positions actually line up between samples of different provenance? So what I've done here is I've prepared 2 plots, and I'll show you them one at a time. Both plots show the position of each band, in this case first the 5.6 micron band with respect to olivine composition, and then I've plotted this up in wave number, and then the colors of the plot of the different symbols corresponds with the different suite or planetary provenance of the material. And so we can observe a couple things first, which is that when we plot the data up in this space, there is still this strong systematic relationship that is also monotonic between magnesium number or iron composition and the band position of the 5.6 band. And then what I've done here is I've plotted up 2 linear regressions with a break-in slope at about forced right 70. The linear regressions are fit to the data from the SUNY suite because that was sort of the nominally purest suite of samples that I had. The break-in slope is based off of first just an observation that there's a subtle difference in slope but at around forced right 70. This is also based off of observations that, from Melissa Lane's infrared data, that there's a break-in slope around this 0.2 in this plotting space. So the other thing that we see is that for both the 5.6 micron band and the 6 micron band, that there's also a strong degree of similarity between the band minimum positions of the synthetic data of the synthetic suites and the natural suites. And then one thing I also wanted to mention that I didn't point out before is that I put error bars on the 2 Apollo samples because there's a range of compositions that are given for these samples where the likeliest composition is highlighted in the darkest green. So what I want to, so the key takeaways from this are that band depth and position, but especially band position, very systematically with iron content and olivine in this 4 to 8 micron spectral crossover region of the infrared. And I think that this spectral range is promising for remote sensing analysis of olivine composition and potentially other silicates, pyroxene and plagioclase, which are currently under study. And one other thing that I think is especially important to take note is that as detectors potentially come under development for this region for the prominent 6 micron band, it's important to understand what other silicate-related bands might be superimposed on this for understanding volatile distribution on the moon and other bodies. And then just some next steps include further characterization of olivine and then a suite of Apollo samples plus pyroxene and plagioclase. So I'll leave this up here just as sort of some food for thought, and I gladly welcome any questions or comments you may have. Thank you.
Hi, Chris. Paul Lucy, University of Hawaii. I noticed your spectra that you showed, some of them had very strong 3 micron bands. How can you exclude some of these features being due to molecular water?
Oh, the 3 micron features? In which plot are you referring to? 3 microns?
One of your early plots, you showed the near infrared. So this one, you have prominent 3 micron bands in the left, which suggests that if there's molecular water present, it would be exhibited at 6 microns. So how can you exclude water as contaminating your results?
Yeah, that's a good question. So so first off, the thing to note is that these are just spectra that I pulled sort of schematically and are not representative. These spectra are actually not examined in these plots later on as just sort of for demonstration purposes. In order to make sure that I was not including any sort of water bands in these data, I looked at the 3 micron band just basically to see is there something that sort of qualitatively and subjectively I would say constitutes a strong 6 micron feature. Mm-hmm. The other thing that that can be taken as some reassurance that the water is not a major contribution is that where the 6 micron band is that the 6 micron band itself shifts systematically with iron composition, which we would not expect in the absence of a strong silicon oxygen bond related feature. Yeah. Thank you.
Got time for one more if anyone has a question. Okay, well, if there's no